So on this lesson 8.6, what we're doing is we're comparing linear, exponential, and quadratic functions. All function families that you already have worked with this year. Okay, so all we're doing today, no really new material except for one small detail, is bringing in these function families that we've spent a lot, large percent of the year on, and bringing them and just working with them together and making sure that if I gave you an equation, you can look at that equation and its characteristics and be able to tell, oh, I know that's exponential, or I know that's a quadratic, or I know that's a linear. And that same thing, if I hand you a graph or data points that you can put on a graph, that you can create that graph and look at the characteristics of that graph and the shape and say, okay, yeah, I know this is linear, this is quadratic, or this is exponential. And so I expect that this first part of it is probably, I assume and hope that it would be really easy. That if I gave you a linear equation, that you would know that you're looking at a linear equation. If it's in that y equals mx plus b, or even in that point slope or standard form, that you know that if it's just an x and you don't see an exponent on it, it's just a regular x term, that's going to be a linear equation. Okay, and that if you are given a quadratic, that you know that the main characteristic that makes that quadratic is that x variable with degree 2, and that is the highest degree of the whole polynomial, so that makes that quadratic. It may have all three terms, like this one here on the example, a trinomial, but it might not. It could be as simple as x squared. That's the parent quadratic. As long as that x squared is present, that is what makes it a quadratic and gives it those characteristics, right? And this is the one that we did kind of end of November and through December, where the exponential functions, and that the really characteristic quality of that exponential function is that x is that x is the exponent, right? Where in a quadratic, the exponent is always 2, and our input is that x base. In an exponential function, our exponent is the domain. It is the variable that we're inputting into that is changing every time. Okay? Same thing with our graphs. Hopefully, if you see a straight line on a graph, you know that's linear, right? Or if I tell you something's linear, you know that graph is just going to be just a straight line. Okay? Quadratics is what we've been working on for several weeks now. We know that is a U-shaped curve. It's a mirror image, so it's symmetrical. It could open upward or downward, but it's a symmetrical U-shaped curve. And then, quick review on exponential functions, it's a one-sided curve. Y'all remember those? Right? It's only on one side. It could be the right or the left, but it's a one-sided curve that is growing, and they grow really fast, right? That is growing really fast on one side, and on the other side, it's approaching that magical line. Remember what that's called? Yeah, the asymptote, right? So on one side, it's kind of growing really quickly, either in the positive or the negative direction, but it's getting quote-unquote large and away from zero really fast. On the other side, it would be approaching a limit. Usually it's 0, but now we'll discuss that in a second. It doesn't always have to be 0, but it's approaching that asymptote value. Okay, so I think this part's going to be the easy part. The more complex part is determining which of these families you are working with when you have just a set of data points on a table or a set of ordered pairs, because that's when we have to look at patterns in our points. Okay, so that's where I'm going to focus most of our time on today. So let's go ahead and practice just the graphing ones first. Once we get to the tables, this is at the heart right here of what we're doing. Okay, the first two we've already done, so that's also review. We've already looked at what linear functions do on a table. We know that they have a common difference. They're either increasing by the same number every time or decreasing by the same number every time. There's a steady, constant rate of change. And we can just always subtract the new minus previous to find out if there is a constant difference and what that is. So that's all review. Exponential functions we've done before. Those have a common ratio instead. So instead of looking at the difference between the numbers and how that is increasing or decreasing, we're looking at a ratio, right? That's a comparison by division. If we divide the new by the previous, do we get the same number as if we divide the next new by previous and the next new? So we're looking at a common ratio. When there's a common ratio, then you know that you have an exponential function. The one that is new today, and this is truly the only piece of information that is new today, is how to tell if something is quadratic from a set of data points, okay? And that is looking to see if they have a constant second difference. So you might be wondering, well, what does that mean? Well, we'll see it in just a moment in action, but remember, linear functions is the first difference. So if we take the difference between all the numbers and find what that rate of change was, if that's constant, it's linear. That's called the first difference. If I check that first difference and I don't get a constant number, but then I do it again, and I find, essentially, I do the process again, and I find the difference of those differences, if that second level of differences is the same all the way across, then that's a quadratic, okay? So that's what we mean by the second differences, or sometimes when you get to algebra 2, you'll hear first differentials, second differentials, same thing, okay? So you'll see that. We'll practice it in just a moment. But basically, it basically means find that first difference, and if it's not the same, just do it again to those numbers, and if that second difference is the same, you know it's a quadratic. Any questions about that? Are we good? Okay, so first, we'll just make sure that we're solid on the graphing. So I'm going to give you guys 4 minutes on my clock, on my timer. I want y'all to just plot the points from 1 through 4 and look at the shape and characteristics of the graph that they are making, and then decide which family they belong to. So 4 minutes. What kind of function do you think number 1 is? Yeah, quadratic, right? So if we plot our points, we've got one point at -3, 2, and then one at -2, 4, and then -4, 4, 1, 8, and 5, 8. So definitely that U shape that we've been working with, that parabola, this is quadratic. All right, I agree. So that's what we got for number 1. How about number 2? If we plot here, we have -3, 8, +1, -2, +2, -1 up to 4, then 0 goes all the way up to 8, 1 would go up to 16. Doesn't quite fit for me. What are y'all thinking? Yes? Yeah, exponential, right? So this one definitely shows that one-sided curve pattern there, so exponential. Okay, how about for number 3? What are y'all thinking? Exponential also, okay, so let's check that. If we have the point 4, 0, that lives right here. 2, 1, 0, 3, -1 goes up to 6, -2 goes up to 10, so we're definitely looking at kind of this one-sided curve, and that is exponential. On this one in particular, I just want to mention, at least earlier, a couple of students said, well, hey, I thought exponentials weren't supposed to touch the x-axis. I thought that was the asymptote. And to some degree, they're right. The examples we did together all had our asymptote at y = 0, which is the x-axis. But just remember that we just spent a couple of days talking about all of these transformations that do things like translate and stretch and reflect our graphs, any kind of graph, right? So hopefully after yesterday's lesson, you realize, oh, you know, me, for example, adding something to the outside of this is going to translate it up that many units. Or subtracting something there is going to move it down that many units. And so if we took an exponential curve and all of a sudden I subtracted it by k units, then down here at -k might be where our curve now lies, because the whole thing just translated down. So a few times back in December when we did this, I told y'all, right now our asymptote is at 0, but it's not always like that. And this is one of those cases. Now that we know there's these transformations happening, we know that our exponential curve could be shifted upward or downward, and that would move the asymptote to other values. It doesn't just have to be at 0. So that might be what happened on number 3. Perhaps, since we don't have the equation, we don't know, right? But perhaps our exponential curve has been shifted down or translated down that many units, and so now our asymptote is at a different number. And it's okay if it intersects the x-axis, right? So that's a possibility. What did y'all get for number 4? Linear, right? Just a nice straight path. When we graph those, we've got 2, -4, and then 0, -2, and then -2, 0, and then -4, 2, and then -6, 4. So definitely just a nice straight line there. So this is linear. Okay, so do we feel super comfortable being able to identify the 3 families or the 3 types of functions if you're given an equation or a graph? Okay, good. So then what I really want to focus our attention on is looking at data, whether it's on a table or a set of ordered pairs, and telling from that. This is where we're going to be looking for things like the first difference or the second difference or the common ratio and trying to find patterns in our data. Okay, so for 5 through 7, we want to tell whether the values represent linear, exponential, or quadratic. And so just a reminder, right, this is just reviewing. If it's linear, it's going to have a constant first difference. If it is exponential, it is going to have a common ratio. And if it is quadratic, it is going to have a constant second difference. Okay? So that's kind of where, you know, the ones that line up with each other. So look at number 5. And just based on the points, always make sure the x is increasing at a constant rate. That's always sort of a, you know, a prerequisite, right, for us to look at the pattern in y. X needs to be sitting, you know, changing at a constant rate. If I'm jumping around on the x coordinates, I'm not going to get valid data on the y coordinates. But the good news is we're not going to throw that curveball at you. At least personally in this class at this grade, you know, this time, we're not gonna do that because it'd be messy and it'd be harder to work on. So you can pretty much trust that we're gonna leave the x values increasing or decreasing at a constant rate, and you can really focus your attention on the y coordinate patterns because that's what we're studying. Okay, so I'm looking at those y values: 7, 4, 1, -2, -5, and we can do all of the tests. We could test all 3 of those, right? But if we're kind of wise about this, we can save ourselves some time. Look at how, is that increasing or decreasing? The decreasing. Does it appear to be decreasing kind of at a constant, steady rate like a line might do? Or do you see it kind of growing faster and faster or decreasing faster and faster? What do y'all think? Seems a little steady and pretty easy going, right? So it might make sense to start off checking for a linear, okay? So when we're looking for that first difference, this is all review, but it's been a while, okay? So if I'm looking for that first difference, I just want to see how much did my values increase or decrease from one y coordinate to the next, right? So what was the increase or decrease every time? So you could either think of that as like, okay, if I started at 7 and I went to 4, I went down how many units? 3, so that's a -3 difference. Or the other way you could do this is do the new minus the previous. So 4 minus 7 is -3. And I know I got that right, okay? How about from 4 to 1? How much did that decrease? It decreased another 3 units, okay? Or in other words, 1 minus 4 is -3, okay? How about here? If I start at 1 and I go to -2, what's that difference? Also a decrease of 3. And last but not least, if I'm at -2 and I go down to -5, also a decrease of -3. That's called the first difference or the first differential right there. And it is constant for this particular data. So case solved. Okay, it's linear because that's what we're looking for when something is linear, or that's the characteristic. So this one's linear. Okay, because the first difference is constant. Okay. All right, so that's why. All right, let's try number 6. Same thing. We're going to look at the pattern in the y's. The x's are going up at a constant rate, so that's fine. Look at what the y is doing. It starts at 2, then it goes to -1, then it goes to -2, then it goes to -1, then it goes to +2. What do you think this might be? Do you think this would be linear also? No, right? I see this decrease up until a certain point, and then it starts to go back up and increase again, right? So which one do you think might be doing that? Probably quadratic. And that'll be nice because this is where you're going to get to see the whole second difference in action, because that's what's really new today is the second difference. So let's try that, okay? So the way that we do the second difference is we really start doing exactly what we did up here. To do the second difference, you need the first difference. Okay, so we're actually going to do exactly what we did up there, and we're going to look for a first difference. Okay, so you would do that if you're checking for linear, or even if you're thinking it's quadratic, you'll need that anyway. Okay, all right. So there's our first difference. Let's check for that, like we did up on number 5. So from 2 to negative 1, what did we do? Decrease by 3, right? Positive 2, or you could think of this as negative 1 minus 2. That's still negative 3, but it's a decrease of 3. Everybody okay with that? Okay. What about from negative 1 to negative 2? Increase or decrease? Decrease by 1 unit. Okay. So, yeah, I'm starting to realize, yeah, that's not a line, right? That decreased 1. And then we go from negative 2 to negative 1. That's an increase of 1. And then from negative 1 to positive 2, that is an increase of 3. Okay. Clearly, our first difference is not constant. So we definitely have confirmation. This is not linear. But in order for me to test for quadratic, what I now am going to do is now I'm going to just do it again and find what we call the second difference. And that's just the difference of these guys. We just basically do it again. Okay? So if we do it a second time and we find the differences of the first differences, let's see what happens. So if you started at negative 3 and then you went to negative 1, that is an increase or decrease? Increase of 2. Okay, good. This is an increase of 2, or you could, again, you could do negative 1 minus a negative 3, which is really just negative 1 plus 3. Still going to give you 2. Okay, what about from negative 1 to positive 1? That's an increase of 2. Boom. Okay, what about from 1 to 3? Increase of 2. And ding, 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 ding. Here's our evidence. Our second differences are constant. Okay, and so that makes this a quadratic. Okay, does that make sense how those work? Yeah. Okay, so there's a couple options. So we just, at that point, we just know, all we know right there is that it's not linear and that it's not quadratic. It could be that it's exponential, or it could just be a totally different type of function or family. Someone in another class period asked, well, what if, is there such a thing as like the third difference being constant? And I said, yes, there is such a thing as a constant third difference. What kind of polynomial function you think would have a third constant difference? Cubic functions. Cubic functions would have a highest degree of 3, have a constant third difference, right? If the fourth difference is constant, it's a quartic polynomial. So imagine that. So yeah, you can, in Algebra 2, you'll get to play with those. And sometimes they give you these long ones and you're trying to, and it's like, oh, it's the sixth difference is constant. That's a 6-degree function. So yeah, so it could be one of those. It could be that it's exponential. It could be just a totally different thing. All that would tell us is it's not linear and not quadratic. So, okay. Let's try this last one, right? So we have a table of data, 1, 2, 4, 8, 16. Does that look like it's linear, increasing at a constant rate here? Now, it looks like it's kind of growing faster and faster and faster, right? Certainly the difference between 1 and 2 is not the same difference as between 8 and 16. Would you all agree? Right? So not linear. We could test for quadratic, or we could test for exponential. Which one do y'all want to test for? Exponential. Okay. Y'all think it might be exponential. So remember, if we're testing for exponential, then instead, this one is a little different. It's really a common ratio that we're trying to find here. Okay. And so what I mean by that is when we start to compare what happened from one point to the next, we're not going to be looking at how much did it increase, but we're looking at a ratio of new to previous. So we're looking at what is 2 over 1, okay, which in this case is 2. What that tells me is that 1 got multiplied by 2 to give me 2. Does that make sense? It's a multiplicative product. If I do the common ratio here, what's 4 over 2? Also 2. That tells me that 2 got multiplied by 2 again, and we got 4. Okay? If we do this one right here, 8 over 4, that simplifies to 2, right? That tells me that 4 got multiplied by 2 to give me 8. And just for safety here, we're going to do the last one. 16 divided by 8 is still 2, which means that 8 got multiplied by 2 to give me 16. So basically, they are multiplying by 2 every time to get the new value. That's the pattern. That makes this exponential. Okay? Okay. So on these right here, I'm going to let you guys practice these, but notice there's one other very key important difference. First of all, our data, they're still giving us data points, but they listed them as ordered pairs instead of giving them to us on a table. It's not a huge distinction, but I personally think it's a lot easier to work off of a table than off of a list of points. They're the same type of data, they're just presented differently. Okay? So what I might recommend, if it helps you, it definitely helps me, and I'm a pro, is that to just go ahead and make a quick table and just rewrite those ordered pairs in a table so it looks more like the problems that we just practiced. The other and probably more important distinction here is that after we decide which function family this data belongs to, they want us to actually write the function. And it's been a while since we've written a linear equation or an exponential equation, so we'll practice that, okay? So let's try number 8. First things first, I'm going to start off by just reorganizing this because I do really think it helps me. I'm not going to require it, but I do think it helps. So I'm going to list my x coordinates, -2, -1, 0, 1, 2. And I'm going to list the corresponding y's, -4, -1, 2, 5, and 8. Okay? I just think it's a lot easier to work off of that. Okay? -4, -1, 2, 5, and 8. Which family do you think that might? Just looking at the kind of the pattern and the way it's growing. I'm thinking linear 2, but let's check it, right? So we're going to look to see what that first difference is and if it's the same every time. So from -4 to -1, that increased by 3. Okay, I agree. From -1 to 2, an increase of 3. From 2 to 5, that's an increase of 3. And from 5 to 8. So we definitely have a constant first difference, right? And that tells us this is linear. So there's our confirmation. That's awesome. I think it's just easier to do that off a table personally. Okay? But the new part now is, okay, well then write the equation that created that data or that corresponds to that data. So now we want to go one step further and say, okay, well if it's linear, then what would be that equation? You know, that y equals mx plus b. Well, that common difference we just found, that increase of 3 every time, what do we also call that in linears? The slope, right? So it's which of those variables? The m value, right? So we already know the m, the rate of change of the slope is 3, okay? But we also need b, which is our y-intercept. So we have two options. If we get lucky, maybe it's already given to us as one of our ordered pairs. If not, no big deal. We've done this a bunch of times now. We borrow a point, we plug it in temporarily, and we solve for b, right? There's no challenge too great for us. But in this case, did they give us the y-intercept? Yes, they did, right? We struck gold here, and it's like, oh yeah, they already gave it to us. So as long as we are comfortable, with knowing that that's our y-intercept and our slope is 3, we can just finish this out and say this is the function. Okay, so just a little review there with slope and y-intercept. Are we okay with that one? Okay, look at number 9. Same thing. I think it's really hard to kind of decipher any patterns where everything's written like that in ordered pairs. So I'm going to do just a quick switch from ordered pairs to table. So again, my x's are increasing steady. -2, -1, 0, 1, 2. My y coordinates are -9, 0, 3, 0, and -9. Okay. Any predictions on what this might be? Yeah, we can kind of see that symmetry already happening, right? But we always want to check, so let's just do those first and second differences. So here's our first difference. Okay, from -9 to 0, that's an increase of 9, which I'll agree. From 0 to 3, that's an increase of 3. Then from 3 to 0, I go back down 3. Or I decrease by 3. And then from 0 to negative 9, I decrease 9. So that's the first difference. But for a quadratic, which is what I'm really testing for here, what I'm interested in is what is the second difference doing. So for the second difference, and if I go from positive 9 to 3, it's a decrease of 6. If I go from 3 to negative 3, it's a decrease of 6. And if I go from negative 3 to negative 9, that's a decrease of 6. So that second difference is my confirmation that this is quadratic. And of course, here's the catch now, right? We still have to write the function. You have a few options here. You know how to write the function from vertex form and from intercept form. Okay, I'm going to notice here that they did give me both x-intercepts. Remember, the x-intercepts are the x-coordinates when y is 0. So that gives me a p and q that I can put into that nice intercept form that we just finished with that we thought was pretty easy. Okay, so if I know that my x-intercepts are at -1 and at +1, I can use those as the p and q in our intercept form. But what other variable do we still need? A, right? So then what we'll do is we'll borrow a point up here. So not only will we know that this will be, +1 and -1, but perhaps I'll borrow another point. Maybe I'll borrow this ordered pair 0, 3, so that I know that y is 3 when x was 0, like that. Okay? And when we clean that up, this is just 1 times -1, which is -1. So I just get -1a is equal to 3. And if I divide that out, turns out a is equal to what, guys? -3. Okay? And the intercept form of our equation is -3, x plus 1, x minus 1. Okay? Usually, though, they'll want that in standard form. So we know that the easy thing to do from intercept to standard is just FOIL it in, right? So if we do that here, I know this is a difference of squares. That's going to save me some time. X plus 1, x minus 1 is a difference of 2 perfect squares. So I very quickly know that that multiplies or FOILs in to x squared minus 1. And then all I have to do is distribute the -3. So the real final best answer here is -3x squared plus 3. Okay. So there's the equation that matches the data. Let's try this last one. Okay, same thing. We're going to start off by putting it in a table. At least that's my recommendation. It's a lot easier to read. We've got -2, -1, 0, 1, 2. This is 1/2, 1, 2, 4, 8. Any predictions based on the pattern there? Okay, so I hear exponential perhaps. What do you think they'd be multiplying by here? So I'm going to look for that ratio. Common. I heard times 2, so let's try it. If we do these two right here, and if I do 1 divided by 1/2, that is 2. Okay, and if I do these two, if I do 2 divided by 1, that is 2. If I do these, 4 divided by 2, that's 2. And a divided by 4 is also 2. So yes, this is exponential. And then we have to write our exponential function. Remember, this is the form for those. Just a quick review. When we're in the exponentials, remember that constant a, that's our y-intercept. And then our base to our power, that's our common ratio, or what we're multiplying by. Okay? So did they give us our y-intercept? Is that one of the points that we were given? Yes. What's our y-intercept? 2, right? So we were given that y-intercept right here. So we know a has to be 2. And then what was our multiplier? What were they multiplying by every time? 2. That's what we got as our common ratio. So our exponential function here would be y equals a y-intercept or starting value of 2 and repetitively multiplying by 2 every time. Those are not always the same number. We just coincidence today. Okay? So quick review crash course. Last one. A ball is dropped from a height of 305 feet. The table shows the height of the ball t seconds after being dropped. Let the time, t, represent the independent variable. Tell whether the data can be modeled by a linear, exponential, or quadratic function. And then, of course, explain, just make sure you show your work. But here's the deal, right? Word problem, lots of words up there, real life scenario. But really the bottom line is we're doing the same thing. We're looking at data points, and we want to know which family or which type of function models that data. So we're running the exact same type of tests here. Okay? So if we go 305, 289, 241, 161, 49, is there maybe one family we can just rule out? What do y'all think? We could probably rule out linear, right? It's likely that the difference between 305 and 289 is not the same as this one over here, okay? So we could test for exponential, or we could test for a quadratic, okay? Which one do y'all think you want to do? I think we just ruled out linear, but so I hear exponential. Let's try it. So if we test for exponential, we would be checking to see is 289. I hope someone has a calculator out. 289 over 5, and is that equal to the same thing as, for example, 241 over 289? Would that be the same as 161 over 241? Are those ratios all the same? What do they equal? Every single one of those gives us 0.9? We're looking for a common ratio if it's exponential. So what's 289? There's like 20 calculators in front of us. They're not all the same? You're getting different numbers for these, right? I'm looking at this. This is probably 0.9, but I'm pretty sure 161 over 241 isn't, you know? So I don't see a common ratio here, but you could confirm that on your calculator. Y'all have the calculators in front of you, right? Can we confirm, yes, that the ratios are not the same? Okay, so exponential's out, okay? And I think we agreed it's most likely not linear, but you know what? We're about to do a first difference to test for quadratic anyway, so we'll see. So let's do first differences, okay? Let's test for that. Okay, what's the difference from 305 to 289? What kind of decrease is that? Negative 16, it's a decrease of 16 there. Okay, what about from 289 to 241? That is a decrease of 48. So yeah, whoever said it was not linear, you were right. That's not linear. Okay, what about 241 to 161? 80. That is a decrease of 80. Perfect. Last but not least, 161 decreasing to 49. That is a decrease of 112. So yeah, we already scrapped exponential, and now we can scrap linear because that's not constant either. But let's check for a second difference. Okay, so now we're going to do the difference of these guys. If you go from negative 16 to negative 48, how much did that decrease? Negative 32, right? It's a decrease of 32. Okay, what about from negative 48 to negative 80? That's a decrease of 32, or negative 32 here. Okay, what about from 80 to negative 112? Ah, look at that. So we have a common second difference, which confirms that this is quadratic. Which honestly, we had already talked about most free fall problems being quadratic in nature, right? That acceleration of gravity, all those free fall problems. Y'all remember that? So, all right, but this confirms it because we can see the second difference is constant. All right, are we feeling okay with being able to tell the different function families?